This video is on Newton's universal law of gravitation. It is the third video on topic 6, circular motion and gravitation, for IB Physics. This topic is part of the core material, so it's the same for both SL and HL students. Take a moment and read the success criteria that we will cover in this video. Okay, Newton's universal law of gravitation. So the equation I have here is from the data booklet. But really, what does it mean? Well, we've got this force due to gravity, and we know it's going to be an attractive force, and it's between any two masses. That's what the reference to universal is trying to say. Now, if you think about it, it should be the bigger the mass, the bigger the force. And true enough, in the equation, you can see in the numerator, we have the two masses, a little m and a big M. It really doesn't matter if one's bigger or smaller than the other, but a lot of the times we say the capital M would maybe be the mass of the planet and the smaller m being the mass of a satellite. One thing to point out is look in the denominator. That's where the radius is found. That means as the distance between the two center of masses increases, the force between them is going to decrease, and it's squared. This is an example of the inverse square law. So twice the distance causes the force to decrease by a quarter. Now, I said the distance between their centers there because technically this should be the distance measured between two point masses. So how can we assume that the objects can be approximated by a point mass? Well, there's two big reasons. One is if the size of the mass is really small compared to the distance between the two centers, then we can assume it can act like a point mass. Another thing would be is if there was a uniform density, meaning the center of the mass will actually be in the center of the object. Another thing to think about is this is an example of us being able to use Newton's third law. The force on each mass will be equal in magnitude and opposite in direction. Right? Now remember, the force doesn't always have the same effect. A bug hitting my windshield of my car will have the same force acting on it as the windshield, but there's a very different effect between the effect of the bug and the effect of my windshield. Now we haven't talked about that letter capital G, the universal gravitational constant. There's a scientist named Henry Cavendish in 1797. He set up an experiment with two large masses and two smaller masses using a torsion balance, like you can see in the diagram there. When the two smaller balls on the torsion balance were let go, the attraction to the larger masses eventually caused it to twist, and the torsion in the fiber has a force on it, and eventually that would balance out with a force due to gravity. The mirror in there was to accurately measure the angle of rotation, and so he was the first one to come up with a value of G. And you can see there that I've got the data book value. Yes, we can find it there as 6.67 times 10 to the minus 11, and notice the units. Crazy, so always double check, they're in your data booklet. You don't actually need to be able to talk about this experiment. I've included it here just to give you an idea of how they could be measuring these things even here on Earth, and we'll expand it to planets and, well, universal, right? Any two masses. Okay, now it's kind of weird. I kept referring to that as big G. So large G, capital G. That is going to be our universal gravitational constant. But we've been using this little g for a long time now, right? 9.81 meters per second squared. So how are they related? Well, take a look. We've been using this equation, F equals mg, and it looks very similar there. So little g must be this value right here. So I've got on here the mass of the Earth and the radius of the Earth, and let's go on and substitute those in and see what kind of value we get. This is a really good time for me to remind you about using the scientific notation button on your calculator. If not, you have to start putting this in with a lot of brackets. On your Texas Instrument, it's labeled as EE. So then you only have to put 6.67, then hit the EE button, -11. It's really good because then it treats it as all one number. If not, what happens sometimes, especially when people go divide by in the denominator, you have to have brackets around the 6.37 times 10 to the power 6 and then squared. If you put the numbers in your calculator, I actually get 9.83. And so you might be saying, well, wait a second, we use 9.81. What is the difference there? Why am I not getting the exact value? Well, the thing is, this value isn't actually constant. And I want you to pause and think for a second. What actually could cause these differences around the world? Now, hopefully you've started to think about things like, for example, what about the elevation? The other thing is the Earth's not actually a sphere, so I've approximated it here as if it's being a circle, okay? And we know that this Earth is actually fatter at the equator and skinnier at the poles. Another thing I want to point out is I just wrote there meters per second squared. And this has a lot to do with in topic 2. We are talking about little g here as being the acceleration due to gravity. But we can actually also call it the gravitational field strength. And in fact, if I move that equation around, F equals mg, that means I've got force per mass, or newtons per kilogram. What I want to show you is those are in fact the same thing. So if I have a newton is a kilogram meters per second squared, if you think of Newton's second law, which is mass times acceleration. And then I'm going to go and divide that again by kilogram. That gives me meters per second squared. So I can call this little g either the acceleration due to gravity, or I can call it the gravitational field strength, the force per mass. Okay, so what I want to do is give you an example of how to use this. So let's see. A small sphere x of mass m is placed a distance d from a point mass. The gravitational force on the sphere x is 90 newtons. Sphere x is removed and a second sphere of y of mass 4m is placed a distance 3d from the same point. What is the gravitational force on the sphere? Now remember, this kind of question is very common because if we do multiple choice, we don't get a calculator. So you're going to do a lot in terms of using ratios. So let's go ahead and set up the ratios. So if we have the first one, let's think about the force here. Gmm over r squared. And if we do some substitution, and we've got a mass, and that radius is actually the letter D in our question. For the second one, now let's go and add in this case, our mass is 4m. And our distance is 3d. Make sure you put it inside the brackets because that does get squared. If I bring that out and put all the coefficients in front of it, you can see here that I've got now 4 over 9 times these letters, which are exactly the same as from sphere x. Now in the question it told me sphere x was 90 newtons, so I've got 4 over 9 of that, and again without my calculator I can do this math. That's 40 newtons. So what does that tell us? The answer is D. All right, let's use another example with the International Space Station. I've used these data coming from, of course, Wikipedia. So let's start gravitational field strength, that's little g. Here's my equation. And there's the numbers I'm going to have to put in. Notice that the radius here is the radius of the Earth plus the height to the International Space Station. This happens a lot in this unit, especially when we do topic 10 for the HL. They a lot of the times give the distance as measured from the Earth's surface. So our total distance is the radius of the Earth plus 408 kilometers. Take a look at the units, make sure they match. And I hope you got the same answer as me. 8.8 meters per second squared, or newtons per kilogram. Okay, so let's continue with this. Part B. What is the centripetal force on the International Space Station? So centripetal force, because let's assume that the International Space Station travels in a circle around the Earth. So it'll be the force due to gravity that's going to cause our centripetal force. One of the reasons it's about 400 kilometers above the Earth's surface is that the atmosphere there is very low, so it reduces the amount of drag. Nonetheless, it's still actually adjusted every year because this isn't exactly zero. Okay, so force centripetal equals the force due to gravity, and we're above the Earth's surface, so we have to use the universal law. Or wait, we already found the new value of g up there from part A. Let's use that in part B. No need to reinvent it. Notice I cannot use 9.8. So here's our centripetal force. Well, is actually the same as for the cycle of comment. These atoms going around in the wind circle, they're constantly accelerating, right? Centripetal acceleration. It just so happens that that acceleration towards the center is the same as what their surroundings are doing, so they actually have the appearance of weightlessness. Now that vomit comet, I can't remember the actual name for it, but you can go up in an airplane, and the airplane will go high enough that it can go into basically free fall towards the Earth. And at that time, as you're falling at the same rate as the airplane, you actually don't feel like you are moving in comparison to your surroundings, and it gives you the appearance of being weightless. Okay, part C. What's the work done on the ISS by the force due to gravity? Well, 0 is the easy answer. There's two reasons for this. First, the force due to gravity is going to be towards the center of the Earth. And we're actually moving in a circle around the Earth, perpendicular to that. We know from our equation of work equals force times distance. Force and distance are supposed to be in the same direction. If not, we need to use their components. But in this case, perpendicular means no work is done. Now, secondly, we also know that work is the change in energy. And we've got a couple of things going on here. First of all, we have a constant speed. So what does that mean in terms of energy? It means then that its kinetic energy is also going to be constant. So no change in kinetic energy. Okay. Now we also know that it's going to have a constant radius because we said it was traveling in a circle. That means the gravitational potential energy of the satellite is also going to be constant. That means we have no change in kinetic energy or potential energy. What does it mean? Finally, no work is done on the satellite. Okay, part D. Show that the speed of the International Space Station is approximately 8 times 10 to the power 3. Now remember, we're going to start with the centripetal force equivalent force due to gravity. And in this case, that little m in our centripetal force is the mass of the satellite. So that cancels out in both cases. It really doesn't matter. If I move this around and then get for the speed of the satellite, in the HL, there is this equation for orbital speed, gm over r. Put in our values that we have here, and I get 7,671. Remember, it says approximately, so I show my unrounded answer, and then finally the rounded answer that they've asked for. Another point. Note what that equation actually does. We have v equals the square root of gm over r. That means the higher the satellite, or the greater the radius, that's actually going to cause a slower speed because the r is in the denominator. So higher satellites will have a slower speed. Also, that mass of the satellite is canceling out. It really doesn't matter if we have a little wee TV satellite or the International Space Station or a piece of meteor rock that's rotating around the Earth or even the Moon. Okay, part E. Show that the International Space Station orbits the Earth 16 times per day. Yep, oops, spelling mistake, orbits with an R. Now let's think about this. It's traveling in a circle, and that means we're going to assume it's going to travel at a constant speed. And I really like that because we found it already in the previous question, but it also means I get to use this equation, the nice easy one. If I rearrange that, I'm going to find distance over speed. Now the distance is traveling a circle, circumference 2 pi r, and if I put in all my data, and I use the speed that we calculated in the previous question, remember it's above the Earth's surface, so not just the radius of the Earth. And remember, we do get error carried forward, so if you had a mistake in the previous part, we can still give you some credit. In this case, we do need to kind of show the final answer. So we should be getting 16, so it should actually show you that there's a problem in E or the previous one if you don't get the answer. Now, I've just calculated 5,550 seconds, but the question says, how many times does it orbit the Earth in one day? So basically, I'm going to need to take the number of seconds in one day, 24 times 60 times 60, and divide it by the time it takes for one of the rotations, and that's going to give me 15.6. Again, you put down the unrounded answer and then the rounded one that matches what we're asked to look for. So it will be 16 times in one day the International Space Station will orbit the Earth. Remember, in all of these show that questions, you can't use that value in your calculation. It must show up in your final answer. Okay, so let's talk a little bit more about gravitational fields. Earlier we said little g can also be talked about as the gravitational field strength. That is the force per unit mass experienced by a small point mass. If we're close to the Earth's surface, we've determined that that value is 9.81 meters per second squared, or newtons per kilogram. But we also, in one of our examples, found that the International Space Station has a value of 8.8 newtons per kilogram. So what this means, as long as we're near the Earth's surface, we can use the same value used in topic 2 when we dropped objects from buildings and things like that. But what does it actually mean? So this value can change as we go farther afield. So what does the field look like? You've probably done magnetic fields when you were younger by sprinkling iron filings over top of magnets. Well, we can't use iron filings for here. We have to use a point mass to try and figure out its gravitational field. Now, if you look at my diagram here. I've got all these different arrows pointing towards the center of the Earth. And the idea is if I put a little tiny point mass anywhere around the Earth and I marked which direction it would experience a force due to gravity, it would always be experiencing a force towards the center of the Earth. And if I did a lot of those lines, then I would make them look and they would all point towards the center. Notice that the lines are closer together at the Earth and they are farther apart. They're closer together where they're stronger. And HL will do more of this in topic 10. Now, this is just around a single mass, but realize the universe isn't made up of just single masses, and they can interfere with each other. So in this case, I've got two masses, A and B. Now, the gravitational field strength is a vector quantity because it is a force per mass, and force is a vector. So at point X that I have here in the center, and let's say it's on a line connecting A and B, the gravitational attraction of A and B are going to be pulling in opposite directions, and they may cancel out. It depends on the masses of A and B. If I had a point out here, A and B would actually attract both of them. Likewise, if I was over here, again, A and B would be attracting that point mass as well. So I could get a spot in between up here. Now this would be a lot more difficult because again, we would need some trigonometry. We would break it up into two components, one being parallel to this line connecting A and B, and the other perpendicular to it. Most likely we will have ones where we are like my diagram here with the X in the center. Okay, in our final example, 2 point masses of 16m and 9m are separated by a distance of 2 meters. A point mass is placed between the two masses where the gravitational force is 0. Where is it? Well, let's start off by saying let the other distance be y. So that would be this one right over here. This is going to make our math a lot easier. So we also know that the total distance is 2m, so a little later we'll have 2 minus x will be also y. So at that point in the middle, the force due to gravity is equal. That's what the question gives us. That means we can put these two things together from the mass of the 16 and the mass of the 9m. And if I put our values in and do some canceling out, I get 16 over y squared equals 9 over x squared. Now here's where I have to stop and say, remember, if this was in a multiple choice question, we don't get a calculator. But if this was in paper 2, you would have a calculator. So I'm going to show you two different ways that I would use to solve this problem. Now, the first is assuming I have a calculator. Let's substitute right away our value for y. Remember, it was 2 minus x. If I put it in here, I can cross multiply and I can start to expand the brackets and I get this equation. And yeah, it's a quadratic. So what I could do is go and use the quadratic equation to answer it. Here's what I get when I put in these values. So I get 12 over 14 or 84 over 14. You see I wrote a 0 there because it doesn't make sense to have a negative length. So that just gives me x equals 6 over 7. Now that would be a lot of work to do, and with the square root and things, I wouldn't want to do that without my calculator. In fact, I wouldn't do that even when I had the calculator. I would just take my values of a, b, and c, use the program that's in my calculator and get it to get the quadratic value for me. So the next method I'm going to show you would be something without using the quadratic equation. So if that made you panic, don't worry. Okay, starting with the same equation. Let's actually take the root of both sides. X is now 3 over 4 y. So let's substitute in now our value of y. Notice x is on both sides. This method doesn't give us both roots, but it will give us the correct one. Expanding the brackets and then moving our x's to one side and numbers on the other, we get the value of 6/7. Now this would be the method I would do if I was doing multiple choice. Notice the pretty nice numbers, square root of 16, square root of 9. But the other method would work if I had a question from a paper 2 and they weren't so nice. So I've shown you both examples. So here we are at the end. I would like you to take a moment and reread those success criteria. I hope now that we've seen this video that you can answer all of those things and you can meet the criteria.